Okay.
Okay, so I'm going to try to pick up from the discussion last time, continuing the ideas. And the basic project that we're trying to work on here is to place Kronecker's Jugendtraum about complex multiplication on elliptic curves, especially the case of the Gaussian elliptic curve and the Eisenstein elliptic curves. Place that theory inside the theory of, well, inside Grothendieck-Teichmüller theory, the theory of Grothendieck's designs. You know, so I kind of sketched out very vague plans for that project last time, but now it seems, unless I'm really screwing up, it really seems to be working. So I'm going to start drawing a couple of Gaussian designs here. And they're going to be, we should be able to see that they're not strictly isomorphic as designs, but that they're in the same Grothendieck-Teichmüller orbit. And we will understand how they're in the same Grothendieck-Teichmüller orbit by exploiting Kronecker's Jugendtraum. So first, I'm just going to draw this pair of designs that are not strictly isomorphic, but are in the same. Yeah, and again, these are Gaussian designs, that they're based on the Voronoi tiling of the Gaussian integers. So maybe I'll start with reminding us of what that looks like. So the Coxeter diagram has 3 dots that I'll distinguish by color. And so how does this work? I guess it's 4, 4, is that right? That seems right, right? Okay, so yeah, so I think I made a silly mistake last time, not realizing the extent to which we can really exploit this idea of Gaussian designs. I drew a few Gaussian designs last time, but they were all very squarish, or they involved modding out by rotation. But I neglected to think about making little parallelograms out of the Gaussian square wallpaper. So this is what I mean. Let me draw some examples here. So I've got, let's see, how does this need? This needs, I'm just trying to figure out how many squares I need on a side. Let's see, 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6. Okay, let's try it like that. Okay. In the middle. And I hope I'm getting I'm hoping I'm using my color coding somewhat consistently here. Am I doing this right? Let's see. Really got to check my picture here.
Can you remind me about, so there was some matchup between red, green, and blue.
Yes, that's what I meant to say.
And 0, 1, and infinity. And since I don't have colored pens, I've been drawing.
Yes.
Drawing 0s, 1s, and infinities.
Okay. Okay, that's not particularly important. You can use whatever one you prefer, I think. But I tend to use infinity for blue. Yeah, I think for some strange reason, I have in left for right here, I have 0, infinity, 1.
Uh-huh. Is there something else that's more important?
Well, just that when I draw the Coxeter diagrams like this, it's the dot over on the right that those vertexes correspond to the barycenters of the Voronoi cells. And this is the Voronoi, this is all based on the Voronoi tiling of the Gaussian integers. So you should think of the reds as the Gaussian integers themselves. It doesn't matter too much where you put the origin. You can put your origin at like the bottom left of this thing. Well, anyway.
Yeah.
And well, so far I'm not really fulfilling my promise to show you parallelograms. I mean, this is really just a rectangle. But in a moment, I'm going to show you a parallelogram, or more precisely, an elliptic curve with a parallelogram fundamental domain. That's not just a rectangle thing, which is going to be in the same Grothendieck-Teichmuller orbit as this, I'm pretty sure. And I'm also pretty sure it's not in the same isomorphism, strict isomorphism class. So what's this second one look like? It looks like it's like one red dot there, and then something there, and then another red dot there. And then what color is that dot? Looks to me like a blue. Is that really where you go? So let's see. Okay. Maybe it's a blue dot right there. And then maybe a red dot down here. Maybe a red dot down there. Maybe that's another blue dot there.
Is it supposed to have the same area as the other one?
I believe yes. And I found that I had a little bit of trouble believing that. But, it's, unless I screwed up, it should be straightforward to determine that it has the same area. And now it's just got the same. It's just got the same grid background. Meaning what? That it goes like that, like that, like that. Like that, and like this. All right, and now I got to finish putting in the colored vertexes here. All right, looks like there's a couple of. So far, I've only drawn one red vertex because when you wrap up the parallelogram into a torus,
right?
So there should be 3 red vertexes, just like there is on the right-hand side.
Right.
And some greens. Boy, is that really where a green goes? I guess it is. Okay. That was green. me just see if I can get this. So this cloth, okay, you can't see that I'm using a cloth here. So the cloth doesn't erase, it just kind of cleans the screen. I get these anxieties about crossing between the physical world and the virtual world.
Uh-huh.
Now, is there anything? Let's see. Is there some grid or something on this cloth? No, pen. No. All right, sorry. Minor pen problems. Blue there. Blue there. So it looked like I caught all the vertexes. So we can do a quick count of the reds and blues and greens, see if we got the same number. Does that prove that it's got the same area? Some sort of Pick's theorem or something like that.
Yeah, I was thinking about Pick's theorem. I think we could use Pick's theorem with just the reds. And
yeah, perhaps.
Because it just needs to have the corners be reds for Pick's theorem to apply. So I think I was trying to do that. I was trying to remember Pick's theorem, so yeah, I was counting like the corners is like I don't even know if I remember Pick's theorem, but if you
me neither. But we can fake it. Yeah, go ahead.
But it's sort of, when I started doing it, it started being the same thing as counting in this case, it was like the same thing as counting the number of reds in the elliptic curve. So like counting ones that are on a corner is like a quarter of a.
Oh, yes.
Yeah, and the ones on the edge is a half. So anyway, yes. So I started deciding didn't need to remember.
That's right. Yes, this is like, some easier version of Pick's theorem. So maybe first I should ask, can you convince yourself or convince me one way or the other whether these are strictly isomorphic or not isomorphic as Gaussian designs? As designs? As
is that the same as elliptic curves?
As well, well, that's a good question. Did I even think about that? Whether they're the same as elliptic curves? I guess that's one of the things I forgot to check, whether they're even non-isomorphic as elliptic curves. And now that you mention it, I guess they probably are non-isomorphic as elliptic curves, and that maybe that somehow ends up being equivalent to what I was asking. But I was just asking whether there was, a combinatorial isomorphism between these tilings, these tiled toruses, and so yeah, I strongly suspect, now that you mention it, now that I forgot to think about it, that they are non-isomorphic as elliptic curves. But I was hoping we could just convince ourselves that they have to be combinatorially distinct. Can I give? Do you want to? Should I just give my argument, or do you want to think about it? Give an idea.
Why don't you? Let's see.
Okay. I mean, I hope I'm right. I hope they're not isomorphic. That'd be annoying if they are isomorphic.
Do they have the same number of 3 torsion points, or is that 2? I mean, that's a crude. Maybe that's a crude 2. Wait, that doesn't mean. Maybe that's like stupid. Never mind. They always. Well, let's see. These are like rational 3 torsion points. I don't know.
Yeah, I think these are 3 torsion points or something. Well, no, I don't know. Okay.
The red ones like the 3 torsion.
But yeah, but you're telling me it's not all the 3 torsion points?
No, that's too weak. Never mind. They obviously do have the same. I don't know. So what are the other ways to tell that?
Well, I was thinking that if you unfurl these, if you take their flat universal cover, then you've got this sort of Gaussian wallpaper lattice, but it's superimposed against the period lattice. You know, the period lattice for these tiles. So, right, so you have two different kinds of tiles superimposed against each other.
You mean the little square tiles and these big things that he drew?
Right. Now the, you know, now the tile shape is not, of course, necessarily preserved, but the period lattice is preserved, right? I mean, you just have to show that, you know, this. So what I'm claiming is that the period lattice and you know, the period lattice and the Gaussian period lattice are very orthogonally, very rectilinearly placed, very rectilinearly oriented to each other over on the right-hand side. But I'm pretty sure that the period lattice over on the left-hand side is just not rectilinearly oriented in that same way to the Gaussian period lattice. I hope I didn't fool myself about that, right? Isn't there? As we draw some more pictures, we may get more clarity about whether or not these are strictly isomorphic. But I really think that they're not strictly isomorphic, and that the reason I gave is basically legitimate.
If you can,
you know, so it's like, right, it's the wrong double coset. They're different double cosets for these lattice orientations or something like that. The orientation of the period lattice to the Gaussian period lattice.
I'm struggling to draw this thing.
Sure, that's fine. And yeah, I certainly struggled at first, but you know, after a little practice, I could draw them a little bit better. So, you know, so far I've just kind of pulled these out of thin air and claimed that they have this property of being not strictly isomorphic, but being in the same Grothendieck Teichmuller orbit. But why do I believe this? Why does Kronecker's Jugendtraum nearly persuade me of this? You know, I mean, if I really understand Kronecker's Jugendtraum as well as I hope I do, then I really think it tells me that these are in the same Grothendieck Teichmuller orbit. So how did I come up with this pair? That's a good question. You know, how did I come up with this pair? So that's the question I should address now, right? Is where did I come up with this pair? So, okay, so what did I do? Well, I started out with the one on the left, not with the one on the right. And I was searching for something that would be equivalent to it, you know, be in the same Grothendieck Teichmuller orbit. So I guess I, you know, wrote down generators for the period lattice on the left. So where should, maybe I'll put the origin over on the left. And it looks like the generators of the period lattice are perhaps 1 plus I and 2 minus I.
Looks good.
And oh, but right. And you know, this period lattice is not a module of the Gaussian integers. It's just a it's not an ideal in the Gaussian integers. It's just a an additive subgroup of the Gaussian integers, and that's why we need to do this generating thing over the integers, not over the Gaussian integers. And that's why we
Mhm.
need two generators instead of one generator. So it's the generators of the period left. And yes, and then somehow, well, okay, so right, so this is not a regular Gaussian design, right? It's not a
What does a regular mean?
whenever you're dealing with any of these combinatorial things that are secretly about group theory, the normal, you've got transitive actions correspond to subgroups, but roughly speaking, but if they're not normal subgroups, then they're all so each different point in the action has a different stabilizer subgroup. So that you have a non-normal stabilizer. But if you have a normal stabilizer, then all the stabilizers are conjugate to each other. And if you think about that, that means that that there's this regular symmetry, that the symmetries of the design itself.
Sorry, you said if you have a normal stabilizer, then all the stabilizers are the same, right? Not just conjugate to each other.
Right, they're always conjugate to each other.
Right. Yeah.
Even when it's not normal.
Uh-huh.
And yeah, so right, what I should have said, we can go back on the tape now because we actually settled these arguments now. Right. I thought I said, what do I think I said? That there, yeah.
You thought you said the correct thing.
Yeah, I thought it was the correct thing. That's right.
Okay.
But
okay.
I don't even care whether I said the correct thing.
Right.
Because you should have understood it anyway, even if I say the incorrect thing. So, yes. No, I can see where actually saying the correct things would help sometimes. So I'll try that. Although, right, there's the other philosophy, right, that you give the audience the chance to participate by correcting the speaker.
Yeah, that's what I thought I was doing. Yeah.
Okay. So yeah, right. This is still the spiel about why normalness of the stabilizer subgroup is equivalent to regularness of the design. Regularness meaning that it's got this big. The design itself has a big symmetry group that's a quotient group of the original Coxeter group. So it's not just the action is transitive under the original Coxeter group, but it's actually transitive under the symmetry group of the design itself.
Uh-huh.
So it's a regular design. So I mean, you can see that, right? I mean, well, so we can ask for the downward normalization of the stabilizer subgroup, and that's equivalent to the minimal unwrapping of this design, which will make it into a regular design. And so basically, regular Gaussian designs are basically these. Well, unless they're modded out by rotation in some funny way. I didn't really think about that. But they are square designs, right? I mean, right?
I certainly agree that the square ones sound like they're regular.
Yes, and that's all I really meant to say, that the square ones are regular. They actually correspond to a quotient of this Gaussian Coxeter group. So we're looking for a minimal way to unfurl these things, which will make them square. And I guess over on the right-hand side, it's sort of obvious what the minimal thing is.
So why? That's. I mean, I agree it's fun, but why are you wanting to do that?
That's a good question. It's part of my intuition about how Kronecker's Jugendtraum completely accounts for the Grothendieck-Teichmuller theory of these Gaussian designs.
So when you get one of these square ones, that's an ideal. Is that part of the point? One of these.
Yeah, that's part of the point. Yes, that's right.
Yeah.
That's right.
What are these? Is there any decent name for these non-ideal things that sound sort of like ideal, but is weaker?
Well, what I said was additive subgroup.
Okay. Yeah. Okay.
And
okay.
I don't really have a better name, but it's sort of a good question. I mean, I've certainly run into these before, but I'm not sure if I've run into them in this sort of context. It may very well be that I should have been thinking about these all along, but it suggests all sorts of potentially interesting ideas thinking about these subgroups. I mean, I guess you can just think of them ideals, but no, not ideals. So yeah, never mind. Okay. All right. So, I mean, you can think of them as submodules with respect to a subfield, but in this case, the subfield is just the integers. The subfield, subring. So they are just additive subgroups. So right, yeah, right. Right now, I'm sort of trying to remember, how I did this. Well, so one thing I remember doing was, I wrote these. I wrote these two generators in a different way. I sort of wrote them as, like a little 2x2 matrix. And I noted to myself that I hope, let's see, so the determinant, I guess the determinant of this matrix is -3. And that's somehow related to the area of these parallelograms, of this left-hand parallelogram in particular. It must be 3 measured in some units, I guess those larger squares.
Yeah, the red squares. That's the same.
The red squares, yes, the Voronoi.
Got from the pics like the pic like.
Yes. Okay, that's interesting. So we right. So I know that 3 is important here. And then I decide to pick something relatively prime to 3 in the Gaussian integers. And I figured to make it, to make it fun, we should really exploit the Gaussian integers. So I decided, 2 plus I. I hope that's relatively prime to, that's 2, 2 plus I is a factor of 5 in the Gaussian integers. So you can sort of tell that it's relatively prime to 3. So.
Sorry, what's this 5 coming from?
Well, my random choice, my pseudo random choice of thing that was relatively prime to 3 was 2 plus I. And I convinced myself that that was legitimate because 2 plus I is a factor of 5 in the Gaussian integers. And that seemed like a reasonable way of determining that it's relatively prime to 3 in the Gaussian integers.
Okay,
2 plus
so I'm
I.
not supposed to know why you care about this yet, right?
I guess not quite yet, because I'm doing a bad job of exposition here. Well, we're supposed to, like I say, we're supposed to unfurl this this thing to make it regular. There's probably all sorts of ways of doing this. I mean, you could start, right? You could sort of guess that it's going to be a 3 by 3 square. That's, you know, that it's going to, did we already say that? If we take the ideal, right? I mean, the 3, right? The ideal generated by 3 in the Gaussian integers, that certainly gives us a square shape, square fundamental domain or whatever. And somehow, because of the determinant of this matrix being 3, you know, this should be an unwrapping of this parallelogram thing, an index 3 unwrapping, and it will be a regular unwrapping. So it's sort of obvious that it's the minimal regular unwrapping, the minimal regular unwrapping, the unwrapping regularization of this design is this 3 by 3 square. What?
Yeah, I can believe it. Is that were you trying to say that that's related to how like 2 minus I times 2 plus I is wait, something, what is it?
Yes. So because of the relative primeness, 2 plus I is going to give us a sort of crypto automorphism of the Gaussian integers mod 3. I mean, just what I'm saying, it's a crypto automorphism. I'm saying that it's, you know, it's not very visually obvious. It's not like rotating by 90 degrees or something like that. It shuffles these 9 elements. Yeah, so that's a 9-element field. Is that right? The Gaussian integers mod 3 is a 9-element field because, you know, 3 doesn't split over the Gaussian integers. So we've got this 9-element field. And 2 plus I, well, yeah, I'm not taking automorphisms of that field, but I'm taking, you know, multiplicative, you know, inside of this field, multiplying 2 by 2 plus I is a, it's an operator. And I guess it acts by something that's linear over Z mod 3, I guess. But I'm guessing that it doesn't act in a very visually obvious way, that it sort of shuffles things around in a funny way. And so it's going to shuffle this parallelogram shape around in a funny way, and it's going to become a different parallelogram. But so we approached the unwrapping regularization of the design. We approached that in a very lowbrow way. Let's do it in a little bit more systematic way, okay? So like I say, the unwrapping regularization of the design, that corresponds to the downward normalization of the stabilizer subgroup to become a normalizer, become a normal subgroup. So it's really just the kernel of the action, right? The kernel of the action versus the stabilizer of the action. Stabilizer just fixes one point. The kernel of the action fixes all the points. So it's like the intersection of all the stabilizers. So that's why it's a downward normalization rather than an upward normalization.
Yeah,
so it's giving us a what?
I never thought about that enough, or at all. Maybe so. That's like some.
It's really good to think about.
General Klein geometry.
Absolutely. It's very, very important. I mean, one of the
There's
ways that I
like
always. Yeah.
So there's also like an upwards normalization in general. And
Sure.
like 2 ways to get a.
Yeah. There's a lattice of normal subgroups. No, a lattice of. I'm not saying a lattice of subgroups. Yes.
Yeah.
And yes, you can upward normalize. Yeah. But one of the questions is, right, what is the upward normalization good for conceptually? And it's probably good for something, but I can't remember. If it is good for something conceptually, I always forget what that's good for conceptually. The one that's really important conceptually to me is the downward normalization. You know, and that sort of surprised me at first because I was expecting upward normalization. You know, I just usually, you know, I would upward.
Yeah, people talk about this normal subgroup generated by some elements.
Yeah, there's probably some
Oh,
good reason to think
no.
about it, but there's a really good reason to think about this downward normalization. So, right, so instead of taking, right, it's taking the intersection of the conjugates versus taking the soup of the conjugates.
Do you have some good way to think about that for like a general Klein geometry and like a type of figure? So you say like, I got a type of figure corresponds to some subgroup. Now I'm gonna create this new type of figure. Is there like some way to talk that's not too mathy that says like what that new type of figure is like?
Yeah, it's like a so you know, I've got the pen tip hovering over this left parallelogram. So I mean, what am I trying to say? It's like I mean, I'm not sure you should have said not too mathy, because this is a little bit mathy, but it's actually very.
Well, I mainly meant not too much like talking about intersections of subgroups or something like that.
Yeah, okay. So it's like a frame. You know, there's figures and there's frames. So it's like a frame for this geometry, but right, it's a frame only for the stuff you can see. You know, there's all this, you know, maybe, you know, frames for this whole infinite subgroup, but we're just dealing with a finite geometry here, obviously. So right, we're dealing with finite geometry. It's like transitive on the red vertexes, but you can ask Fred for frame for that. So
are you using frame in a
slightly mathy sense?
Wordsworthy sense?
Yes, absolutely. Yes, it's a torture for this quotient subgroup. So it's, you know, it's complete frame information, but only for the stuff you can see. You know, only for the stuff that can be expressed in terms of these red vertexes. You know, so what is a frame here? You could say a frame is one of these little, by the way, so these squares that I've been drawing, these are the lozenges, right? They're actually subdivided into the triangles, the Coxeter triangles. If, right, the Coxeter triangles are like that or something like that. Did I say that right? No. Okay, that was the wrong one. So it's like that. Those are the Coxeter triangles, right? And in fact, those are the frames, right? Okay. So, right. Am I claiming that there are 9 of the, well, I think there are 18 of those. Those are the 18 frames for the Coxeter reflection group. So there are just 9 of these. There are 9 of these lozenges. So yeah, I mean, let me act out a calculation that will help you here. But I am saying that, right? It's like we're saying that, you know. So what are we saying here? We've got a. Yeah, this is a little bit confusing, I admit, but I think there's this frame regularization unwrapping is always got as many red vertexes as the original one had lozenges, as the original one had squares or lozenges, these quadrilaterals.
Wow, I'm really confused. Isn't that just twice the number always? Wait, as many vertices as the original one had? Say that again. Sorry, it has as many whats as the original one had.
Boy, you've got a really good. Yeah, you're okay. Did I say something stupid? Let's see. So
I just didn't hear it. I mean, I don't know. Maybe it was stupid, but
yeah, no, okay. I didn't say it right. I didn't say it right. So okay. So what am I trying to say? No, I don't think I said it right. I don't think I said it right. So what is it? What is it? What is? I mean, it's the frames for the geometry.
But it's got to be 3 times as big in some sense, right? Or am I really mixing?
Yes, yes.
So it can't just be like a matter of like triangles versus lozenges, which is gives you always a factor of 2. It's got to be something that like depends on the shape.
Yeah, okay, right. So that part was silly. So what am I trying to say? How do you get a frame for this geometry? I mean, maybe we have to invent an ad hoc notion of frame for each individual example. But what am I trying to say? So, right, if I nail down one of the reds, is there any symmetry left?
I don't think so.
Then what am I trying to say? All right. Maybe I'm not saying this right. Let's see. I know there's a really good conceptual answer to your question, but I admit I'm stumbling at the moment. Let me go ahead and do a calculation here, and this calculation will secretly contain the good conceptual answer. So let me do the calculation here. So what am I trying to say here? So over on the right hand side of the screen here, I'm drawing an origin. I'm using this, graph paper background grid now, I think. And so what do I want to say here? I want to draw I think I just want to kind of draw the period lattice of the yeah, what I want to do is I want to just draw the period lattice for the left-hand picture, just kind of all by itself, so it doesn't get too cluttered. So that's that's, I guess, the period lattice. The vertexes of all these parallelogram tiles. And then I want to draw the that period lattice rotated by 90 degrees.
Okay.
And then I want to take the intersection of those 2 lattices, and we'll see what it is. So so what does it look like? It looks like this thing. Yeah, maybe that's my origin there. So that's in the period lattice, and then this stuff is in the period lattice. Is that right?
Yep, looks good.
So it kind of looks like that.
Yep.
Okay, and now I'm going to rotate that period lattice by 90 degrees. And so what do I get when I rotate that by 90 degrees? I get something like and where is it? Over there? I'm doing that right?
Is that right?
I hope I'm doing it right. I'll be annoyed if I'm screwing up. you know, I'm using my chess knight intuition about drawing these things. I guess that's why I always use the Gaussian prime 2 plus I. So where's the intersection of the two lattices? So it's, you know,
Confused about this. If you take one of those, okay, well, you're doing okay.
what were you going to say?
Let's see. So like one of your black points was 2 minus I. So 2 across, 1 down.
Yes, yes.
And then if I rotate that 90 degrees,
Yes.
okay, yeah, so I get 1 across, 2 up. Yeah, okay, that's fine. Yep. Wait,
So,
yeah.
so,
Okay.
so if we think about this, we should be able to say what these things are, what these frames are. So it's like, what are they? It should be, right? It should be some sort of configuration. It's like, oh, okay. Yeah, right. I think the point is that, okay, right. I think we were sort of, what am I trying to say? Even if you nail down a red, am I claiming that there's still some symmetry? What am I trying to say? I mean, I guess I should leave this as a homework assignment for myself, and to really give you a good answer next time, or a good answer in email, because I know there's really good answers to this question, and I'm just not seeing it, just not feeling it at the moment. You know, it should be something like a frame is a red together with the green next to it that acts like a frame or something like that.
Okay, well.
Yeah. There's a really good general Kleinian geometry philosophy answer to this question. I'm just not saying it right at the moment.
Okay. That's fine.
So, but yeah, somehow the answer, the conceptual answer to this really is encoded in this calculation picture over on the far right-hand side. So where are we? So basically, I just let 2 plus I act over in this regularization picture. So, right, how does 2 plus I act on like the black lattice? Is that what I'm saying? I mean, something seems funny about that. I mean, okay. So what am I trying to say? So I've got 1 plus I, and I've got 2. Since I don't understand what I'm doing well enough, I'll have to act it out, and then you can maybe explain to me what I'm doing. Okay.
Okay.
So I've got 1 plus I, and I've got 2 minus I, and then I'm going to multiply each of those by 2 plus I. Yeah, I'm gonna multiply each of them by 2 plus I. Right, okay, right. So I guess part of the point is that over in the far right-hand picture, there's nothing about 2 plus I that's really been incorporated into the picture yet. But anyway, multiply both of them by 2 plus I, so what does that work out to be? So we have 1, sorry, shouldn't write with the highlighting. Okay. So we have 1 plus I times 2 plus I. And we have 1 minus I times 2 plus I.
Do you mean 2 minus I times 2 plus I?
Yes, sorry. Two, what is it? 2 minus I
Yeah.
times 2 plus I.
So that one is 5.
That one is 5. And what is this one over here?
It has a 3I in it, and it has it's like 1 plus 3I.
1 plus 3I. And 1 plus 3I is like I'm just trying to act this out, right? So what am I trying to say? I've got this 1 plus I, but then I sort of make a night move out of it. Is that right? So I go like 1 step, 2 steps, and or let me act it out over here. 1 step. I'm on the far right hand side now with the cursor. 1 step, 2 steps, and then the L shape of the night move. So it's up here. Yeah, it's 1 plus 3I. I just like to encourage myself to believe that I understand the geometric interpretation of multiplication of Gaussian integers. So yeah, it is 1 plus 3I for people who don't even like to look at the pictures. So that's like a larger lattice. Well, sorry, I should never say larger lattice, right? Never say larger lattice or smaller lattice. Always say finer lattice or coarser lattice.
Yeah.
Because
yeah, we used to argue about.
Yes. It's got more points, or it's got a bigger fundamental domain, or something like that. It's got more room for each point. Right.
Yeah.
That's the basic contrast. That's the basic argument. Is
Right.
it bigger because it's got more points, or because each point has more room? So this is a coarser lattice. You can agree on that, right? It's coarser by a factor of, is it 5 or by the square root of 5? Something like that. The fact that
Square root of 5 is how bigger the cells get
in length, but in area, it's 5 times, right?
Okay. Yeah.
So so it's a coarser lattice, but these lattices are all co-compact. So you get these compact things when you roll it up. And something has to give when you're working on this compact thing. It's not going to give you a coarser lattice. It's going to give you it, right? If you sort of, if you're working inside of this compact rolled up thing, then this new lattice is actually going to be the same size as the. So what I'm saying is, take additional generators here, which are 3 and 3i. So we've got these 4 generators here. We've got 3 and 3i. And we look at the lattice generated by those. And it's it's not freely generated, but we can find some free generators for that.
Hmm.
Right. So we're over in, I guess we're over in the far right-hand picture here. Right. We multiplied, I guess, the black lattice by 2 plus I.
Yep.
So it kind of got rotated and enlarged a bit. But after we incorporate the 3 and 3i into it, that will make it finer to compensate for the coarsening.
Uh-huh.
And that's what's giving us this Grothendieck Teichmuller thing.
Uh-huh.
So, I mean, Kronecker's Jugendtraum says that the absolute abelian group of the Gaussian field, did I say that right? Absolute abelian Galois group. I always forget to say, yeah, the absolute abelian Galois group of the Gaussian field is all about these torsion points and stuff. It's all about how these things that, when you take the Gaussian integers mod 3, that kind of gives you a picture of the 3 torsion points on the Gaussian elliptic curve.
Yeah.
And the absolute Galois action on the coordinates of those points, according to Kronecker's Jugendtraum, is basically the Kronecker's the absolute Galois action on the coordinates of those torsion points, those 3 torsion points, is the action in the Gaussian integers of multiplication by these things that are relatively prime to 3 in the Gaussian integers. That's kind of what Kronecker's Jugendtraum is telling us. I mean, they sometimes phrase it in different ways, but that's the way I think of it. I mean, there's probably better ways to say it, but I mean, I'm still fumbling through this here.
Yeah, I'm not sure I ever heard it that way.
That's much more like the way it really is than saying that, that these extension fields are generated by but it's the same thing. It's the same thing, right? I mean, so you're saying something like, you're alluding to some conventional thing where they say that that these abelian extension fields of the Gaussian field are generated by the coordinates of these torsion points on the Gaussian elliptic curve. I think that's what you're saying. I mean, yeah.
I'm really weak on this Jugendtraum stuff, so I don't know if I was even saying that, but
well, I mean, sometimes people talk about the Kronecker's Jugendtraum actually involves a mix of looking at the torsion points on the Gaussian elliptic curve and also looking at the points on the moduli stack of elliptic curves. There's a mix of these 2 levels, looking at the torsion points on the elliptic curve, but also this higher level moduli stack thing where you look at so I'm focusing, there's like 2 halves of the Kronecker's Jugendtraum, and perhaps I'm focusing on the half that you think about less or that you've heard less about.
I think so, yeah. So sometime I'd love for you to just tell me about that stuff. You're sort of.
I mean, this is the more basic thing. This is the more basic thing. So you're hinting at something that involves fields or rings of algebraic integers that have non-trivial ideal classes, non-trivial ideal class groups. The Gaussian integers has a trivial ideal class group. So that, that extra fancy thing that you're alluding to doesn't even enter into the story here. When you were just dealing with the abelian extensions of the Gaussian integers, if I understand what you're hinting at.
Yeah, I think so. So could you say again the thing that you said about the way to think about it for this? So this thing you're about to tell me is like supposed to be
right. So you're saying something
general for ones without an ideal class, the trivial ideal class group, or is it supposed to be true for all quadratic extensions?
We're getting into so many side questions here.
Well, you just sort of offhand. I'm not trying to.
I mean, I have a feeling that you're saying something like that you're thinking of something like, certain. Right, there's like the Hilbert class field of a field, which is it's like an unramified extension. But here we're dealing with, ramified extensions. It's funny that we're dealing with ramified extensions of the number field, but we're dealing with unramified extensions of the elliptic curve. That's kind of funny. I don't understand that. But so I mean, there's some famous thing that says like the Hilbert class field of a imaginary quadratic field is generated by the values of the Klein's modular invariant J function or something like that. The values of Klein's modular invariant J function at the ideal classes of the group or something like that. But like I say, the Gaussian integers only has one ideal class. It's just the square lattice. And so it's its own Hilbert class field, if I'm not screwing up. So that yeah, right. I guess one way to say it is that you're hinting at some famous thing about unramified abelian extensions, whereas I'm saying that the really nuts and bolts of the whole idea is all about confronting the ramified abelian extensions. And
can you just say it again, or like?
Yeah,
you said
I'll try it. So instead of instead of taking elliptic functions and evaluating them at ideal classes, sorry, I didn't get that right. Instead of taking the modular functions and evaluating them at ideal classes, you take the elliptic functions themselves and evaluate them at torsion points to generate these abelian extensions. And so the generators of these abelian extensions, those have to be things that get moved around by the Galois group. That's the whole idea, the whole way of how Galois theory works. That the extensions correspond to the Galois subgroups. It's this contravariant way. So these things that are generating the extensions should really be getting moved around by the ideal class groups. And the way they're getting moved around is by this multiplication by things that are relatively prime to the torsion modulus.
I don't know if I'm ever going to remember this. Let's see. Can I try to say that? I've got to. This may not be
Yeah.
what you wanted to be talking about, but you're trying to connect this stuff. I mean, I sort of see how it's getting connected to
Yeah, I
the
mean,
designs, but I don't even know, but I didn't even know what it was.
right. I mean, but that's the whole plan. The whole plan is that, we've got
Okay.
a dictionary here, and it, explains something sort of complicated, the designs, in terms of something that I claim is easy, the Kronecker's Jugendtraum.
Yeah, well,
But
unfortunately, I don't.
right, but that's the whole plan. The whole plan is that you use
Oh,
the
that's
dictionary to learn the easy thing as well as to learn the hard thing.
okay.
So,
It reminds me
yeah,
of how Lisa was recently reading some poems translated from classical Chinese into Scots.
yeah.
And she was using her knowledge of classical Chinese in those poems to figure out Scots. But anyway, so it's like it's sort of,
So which
tough.
way she was translating? She was translating from.
No, some friend of hers has
Oh,
a nice book. Some guy who lives around here has a nice book of poems from classical Chinese. Some Du Fu, a
yes,
specific poet,
yes,
translated into Scots because he's like a pro Scots kind
yes,
of guy who lives.
yes,
I'm in
yes,
Edinburgh
yes,
now. Yeah.
yes.
So Lisa's some Scots you can sort of almost read if you know English, but then there's like some of it.
Is this the person whose house you're living in that has the Chinese?
No.
Oh,
This is a friend of Lisa's who happens to live near Edinburgh.
okay, but apparently Chinese is very popular in Edinburgh. Okay.
Well, there's just lots of people in Edinburgh.
Okay.
And so,
Well, because it's Lisa's fault, right, for hanging around with Chinese people. Okay.
right, yeah. So it's selection bias here, but
Sure.
so anyway, this guy has this nice book, but so if you try to read these poems in Scots,
Yeah.
if you're an English speaker, it's very strange experience because like maybe like 3/4 of the words are sort of like English words and some you can't tell at all. So she was trying to use her knowledge of the Chinese poem, the poem in Chinese.
Sure.
Maybe printed on the facing page in this book.
Sure.
To learn Scots. So anyway,
Yeah,
that's
I mean, yes, sure. I mean, we're desperately short on time here, but you're forcing me to mention George Mackey. His maxim was that the best translations, like literary translations, or also like translations from physics to mathematics, the best translations are done by native speakers of the target language, is his philosophy. That must be somehow related to what we're doing here. But it's all right. It's also true that, right, that, when people are trying to give propaganda for learning foreign languages, they always claim that it'll help you help you understand your native language better, which is probably true in some sense.
Yeah.
So yeah. So where the hell are we? Right. So did we say it? So yeah, I mean, I'm happy that you're forcing me to try to say this, because it is so easy and beautiful. I mean, in some ways, I hate just visual thinking. I mean, but there's such a visual picture to this. So there's such a visual picture to it that I do have to struggle to put into words. But there should be a really beautiful, easy way to put it into words. So, but let me struggle with some clunky way to say it again, even though I've probably already said it. So what am I trying to say? That the arbitrary abelian extensions of, for example, the Gaussian integers. I was emphasizing arbitrary because I don't want to just only talk about the unramified ones, because that would be too boring. That's the thing we don't want to talk about. We want to talk about the arbitrary ones, which include ramification. And those are generated by evaluating these Gaussian elliptic functions at the torsion points. And the job of the values at the P torsion points is to be moved around by this element of the Galois group that acts like multiplication by something relatively prime to P.
Okay. Yeah, I don't know this stuff, so.
It's so, I mean, right, okay. Let me struggle once more to say it the really correct way. The really correct way is to say it is that there are these pictures, these donut clock pictures, these toruses with lattices on them. So these are like torsion points on the elliptic curve. It's kind of a meshing of the picture of a donut and the picture of a clock, but it's two-dimensional clock arithmetic, but on a torus. And it's a picture of, and the point is that why would you draw such a silly picture in the first place? Why would you subdivide a torus into these two-dimensional clock points, clock arithmetic on a torus, two-dimensional clock arithmetic on a torus? And there's two reasons. There's two interpretations of this picture. And you're supposed to, when you really understand what's going on, there are two conceptual ideas that are perfectly blended together. And one idea is that you're looking at these quotient rings of the Gaussian integers, and you're looking at the multiplication action of something that's relatively prime to the torsion modulus. So if it was actual clock arithmetic, then it'd be 12 or 144 or whatever, that would be the clock modulus. I guess 12 would be the modulus, but there'd be 144 torsion points on this donut. And so that's one interpretation of this picture of the lattice things on the torus, lattice things on the donut. Is the interpretation is that those are torsion, those are right. I mean, this is the whole idea of complex multiplication, these very special elliptic curves that have complex multiplication. That these lattice points on the torus look like a quotient ring of an imaginary quadratic number field.
Yep.
And so, yeah, there are these two things that have the same visual representation. One is the multiplication action of elements in this quotient ring of the Gaussian integers. And the other thing that has the same visual representation is the Galois action of the absolute abelian Galois group acting on points, acting on the coordinates of these torsion points, Those coordinates of those torsion points are very beautifully algebraic numbers. They're in the absolute, what do they call that? Q bar, I guess. The absolute, what do you call it? The
algebraic closure.
Algebraic closure of Q. Algebraic closure of the rationals Q is Q bar. And the coordinates of those torsion points are algebraic numbers in a very beautiful way. I mean, right? Think about how they are.
Yeah.
Did I say that?
I'm happy with that.
Right,
So,
but I want to say it anyway. And one of the ways they think you can think about how they are algebraic numbers is that you have this whole beautiful story about how multiplication on the elliptic curve, or maybe you call it addition on the elliptic curve, is what is it? It involves tangents and secants or something like that, right? You draw a line through this cubic,
yeah,
and it somehow tells you how to perform this group operation that makes this elliptic curve into an abelian group. And so that that geometric instructions for getting the group operation on the elliptic curve, that translates perfectly into, rhetorical algebra or whatever. I mean, you can translate that geometry into algebra. So you can define the torsion points algebraically, so the torsion points are algebraic numbers. And that means they have to be acted on by the Galois group. So, right, you can define these things algebraically, but you can't define individual ones algebraically. So somehow there's like this shape-shifting thing going on. We can nail down, the first torsion point over here is different from this other torsion point over here. We could, give like, we could look at their decimal expansions and see that, oh, these are clearly different numbers. We know them differently. But a pure algebraic thinker cannot distinguish between these. These are in the same Galois orbit. So there's some mysterious shape-shifting that's going on. It has to do with, characteristic P geometry versus geometry over the complex numbers and over the real numbers and stuff like that. And that's all this mysterious interaction, all this mysterious stuff about Galois theory. And
it sounds like I missed some sessions when you were, they weren't with me, when you were like showing, doing examples of how the Galois action moves around these torsion points.
Right.
Thinking of it in both ways. You sort of started doing it right now, but you were doing it like in the middle of telling me about something else, so it like freaked me out.
Yeah, right. This isn't the first time I've tried to tell you about this, and I've done a really bad job of being organized about it. I've been very disorganized about it. But my excuse is that the ideas are so easy, they're so easy, but so and nice and beautiful, but also very visual. So it is a little bit of work to take that visual thing and turn it into a verbal story, but it's very much worth doing so. So we really should do that. But I'm doing a better job now than I have previously. So it's good. Like I say, this is all, this is all according to plan. This is good that we're doing this. So yeah, this is what's going on here. This is what's going on here. That there's this very simple picture, which is a donut with two-dimensional clock markings on it, so to speak, a donut clock. And it has two beautifully cryptomorphic mathematical interpretations. Or, maybe the thing that has these two beautifully cryptomorphic mathematical interpretations is this mysterious action on those clock points. And the action is a little bit mysterious. It's a little bit shape-shifting. It's like non-continuous or something like that. Maybe if you really understand what's going on, you can see it as like continuous somehow or something like that. But it seems like violent. That's why that there are these different designs. Grothendieck's designs change their shape under the action of the absolute Galois group. And that's what we're trying to understand here. But we're trying to understand it in this very simplified special case that secretly has been understood for 100 years or more than 100 years by Kronecker. And Kronecker called it his Jugendtraum.
So we could.
So the two interpretations are the action by multiplication in the quotient ring. That's one interpretation. The other interpretation is action by the absolute Galois group on these algebraic coordinates of these torsion points. And Kronecker's Jugendtraum is saying that these are secretly the same. And then that other fancier stuff that you've been hinting about the
modular function.
Modular functions, yeah, that comes in when the that doesn't enter into the story until you reach these complications of non-trivial ideal classes and non-trivial ideal class group. And you know, that has to do with when you have these donut clocks that are not coming from, what am I trying to say? There's some complication that, right, I guess the point is that if you mod out your elliptic curve by one of these non-trivial ideal classes, right, then the whole point is that you're not getting the same elliptic curve as if you just mod out by the trivial ideal class. So you're actually getting a family of elliptic curves that are all secretly related to each other because they share, they are different from each other, but they share complex multiplication by the same imaginary quadratic number ring. And but that's a fancier thing. I don't want to worry about that. That's a very entertaining complication that arises when you have to face up to this famous phenomenon of non-trivial ideal classes. I guess that's only semi-famous, but it's linked to this famous thing of what is it? Number rings that lack unique factorization. It turns out that that's secretly equivalent to having a non-trivial ideal class group. So yeah, so we are, yeah. Okay.
So one dumb thing that I guess you've been implicitly saying all along, is it true or that these two, if I make an elliptic curve out of these two pictures that are staring us in the face here, those are isomorphic as elliptic curves. Now I can see it, I think.
Well, which ones are you talking about? I know, I think they're not. Oh, is that what you're telling me?
But you made it sound like you're in some situation where there's like lots of, I just realized, maybe I'm wrong, but it just looks like I can take the one I left and like chop it. I wish I could point at things.
Right.
Chop one of the right, there's these like big fat right triangles sitting in there, made up out of a square and two small right triangles. I could just like chop it up and rearrange it so that I could rearrange this thing so that it was like a big rectangle, 3 by 1.
Well, obviously, this is a fairly crucial question. I mean, I have a feeling that I claimed earlier that they're very likely not equivalent as elliptic curves.
Yeah, I guess I was the guy who like started asking, are they the same as elliptic curves?
Right. I mean, it wouldn't be fatal to the whole story. It would still be a good example if these are equivalent as elliptic curves, because the thing is, I'm pretty sure they're non-equivalent. I'll be really annoyed if they're equivalent not only as elliptic curves but as Gaussian designs. That would be annoying. Let's see. Do I see or understand what you're saying?
I pointed the damn thing.
Right.
Often,
if we were more competent, there's some way I could, let you.
Yeah. Well, I don't think. I don't think.
So
it makes it easy to be that. That should be really easy to do, but.
So, I mean, we're rapidly running out of time, but that's okay because, right, I'm sort of claiming that we have done a lot of what we were supposed to do, right? If everything we're saying were right, I mean, this, if I haven't screwed up horribly, then this is really giving an example that you should, in principle, be able to understand of this whole Jugendtraum as a special case of Grothendieck Teichmuller action.
So part of why I suddenly said, hey, these look like they're isomorphic elliptic curves is, well, part of it is because they actually do look like it to me. But the other reason, the reason why I thought about it is because you started telling me like, oh, we're doing this Gaussian case where there's a trivial ideal class group.
Okay, but let me give you a counter argument, okay?
Okay.
So my counter argument is, right, I'm going to claim that you were trying to trick me here. I hope I'm right this time. So I'm hoping that you were tricking me by just getting the two lattices mixed up. So there's this period lattice, which is right. This period lattice is a sub-Gaussian lattice. But there's you can approximate any elliptic curve by sub-Gaussian. You can approximate any parallelogram by sub-Gaussian lattices. It'll be rounded off to a decimal thing or something like that. But you can get, right? It's not like you're stuck near the Gaussian point in the moduli stack. Sub-Gaussian lattice, and yeah. So this particular, there's no reason to think that this particular period lattice, which is a sub-Gaussian lattice, there's no reason to think that that is itself a Gaussian lattice. So yeah, this one
Why
that's
do you say
generated
this
by,
period lattice is like, I thought all those red points were Gaussian integers.
they are, but this sub-lattice of index 3 is, right, you can have a lattice generated by Gaussian integers,
Oh,
but
maybe I
that
was
looks,
thinking,
but that is a very good approximation to the Eisenstein thing. Right, you can just,
yeah,
you know,
well,
you can build
yeah,
approximate equilateral triangles out of,
yeah, no, but
yeah.
I still think that it looks to me like you can just
Oh, okay,
dissect one of those.
maybe you're
I
right.
wish I could point. So like, for example, what I'm doing in my mind is I'm taking the picture right, the
Yeah.
big, and I'm rotating it 90 degrees. So it's like it's a horizontal rectangle instead of a vertical rectangle. That would be the same.
Well, I could certainly do this for homework. I can check and see if you're
You don't
right.
seem like, okay, you don't
No,
seem like.
I think I almost see it. I think I almost see
Okay.
it, but we're down to like 2 minutes and you have to go
Okay.
like,
Yeah, okay.
so,
Okay. Yeah,
you know, I'm just trying to make sure that we're ending on a sort of punchline here. So my sort of punchline here is I said, I think you're sort of seeing what you're supposed to see here. And it did sort of go, you know, the way we were sort of planning, the way we're sort of expecting, that what you're really learning here is the easy language on the one side of the dictionary, or the less ambitious one, the older one, the 19th century one.
yeah.
Not the 20th century one. So we're finally learning some 19th century mathematics here. Kronecker's Jugendtraum is what we're understanding here, but we're also getting our toe in the water that this is going to help us understand, you know, all this 20th century stuff, Grothendieck Teichmuller theory, and maybe a whole bunch of other stuff. So I think I see the picture you're talking about. I just said, right, I wish you could just take control of the pictures or something like that. But I think I see it, but I have to check it for homework. I won't be able to do it in 30 seconds.
Yeah, okay, that's fine. Yep.
So
well, let's quit here, and yeah, no, it was good.
Okay.
I may understand some new stuff now. Yeah.
Right. I mean, there's probably all sorts of things that I'm forgetting to say, but that's there's always all sorts of things I'm forgetting to say. So yeah, let me just see if I can say it again. There's this one picture, and it has, I mean, there's this one picture, and there's this action on this picture, which is a little bit peculiar because it sort of violently violates the shape. It changes the shape in some sense. I have to understand what I mean by that better. But this action has two different interpretations. This picture has two different interpretations, and understanding that the two different interpretations is like really crucial.
Okay, doke.
It's the whole thing that's going on here. Okay, I'll see you. Bye.
Bye.